So welcome to Energyscape's Lab's latest presentation. This is on preparing the next generation, so building classical space science with the new paradigm. So this is a culmination of the last 5 years of research in the field of unidentified anomalous phenomena and our new science that is behind all this, and it's resulted in looking at our space science education curriculum and building on the foundations of that with the new paradigm shift in thinking that is upon us now around the world. So a bit of background behind that. So I am the owner and founder of Energyscape's Lab, which is a lab looking at unidentified anomalous phenomena, research and technology development and reverse engineering. Now behind that I have a PhD in environmental and marine science, a graduate certificate in strategic studies and a graduate diploma in education. And then I'm an accomplished science and technology author. So I've got a science fiction novel series out set in the deep sea mining industry and a plot around the rollout of reverse engineered UAP technology. I'm an experienced science educator, having taught at University TAFE and high school. Experienced research scientist, I worked in the resources industry in fisheries and aquaculture, oil and gas and mining, and environmental management as an environmental advisor. Industry experience around all that as well, and military experience, and of course teaching experience. So this presentation is based on a white paper we've put out recently called Bridging Classical Space Science Education with the New Paradigm. So preparing the next generation now discussion paper, and there's a companion document that goes with that called Bridging Science Horizons. Now that's a companion guide to future ready space science curriculum discussion paper. So the two are closely linked. The companion document really builds out how we bridge space science curriculum with this new paradigm and provides a pathway to achieving that through the education sector. So just to introduce the presentation, we've got here why space science education matters now, the core message behind that, and we concentrate on the fact that foundations still matter and what's emerging at the frontiers of science. So we look at how those two are linked and follow on from that by talking about the integration challenge and the strategic framework around that we've discussed in the white paper, and then the role of educators and institutions in realizing this and implementing it and preparing for new industries. So it's really important now, because this is upon us now, this emergent paradigm, how we prepare students for roles and pathways into jobs that are going to exist in the very, very near future. So we need to prepare for that. And we look at the companion guide overview, so a little bit more detail about just how we link the current space science and subject curriculum with this new paradigm, and then a call to action and conclusion. We've just got here a little excerpt from some work we do at Energyscape's Lab. So this was a UAP that was spotted or observed over Perth not long ago, and we looked at the video and did some frame and image analysis on it and wrote a paper on it, a technical paper on it, and published it, and looked at the mechanisms and the technology behind this, irrespective of its origin, and how the mechanics work and what the implications that has for reverse engineering and new technology. And then on the left here, we've just got this nice little graphic here of the paradigm shift in science and technology that's upon us now, and looks at how the curriculum is going to, I would say, have to incorporate this new science, and maybe not new science, just publicly accessible science now, in scalar propulsion technology, and the implications it has across all our traditional sciences, really: biology, chemistry, physics, maths, engineering. So we came up with 3 core areas in the white paper about why space science education matters so much now, and the importance of bridging foundational learning with the new paradigm. So we've got preserving core scientific foundations. So the fundamentals of physics, electromagnetic theory and orbital mechanics are essential for building scientific reasoning and learning how to apply the scientific method. Then secondly, we've got a new era of scientific possibility. So students must also grapple with fields that integrate energy, consciousness and matter in novel ways. And that is really starting to gather momentum in the private sector, in industry, defence and aerospace now. So there's quite a need, I would say an emergent and urgent need to address this in our education sector. And then there's an urgency to act. So the curriculum must evolve now to prepare learners for a fast changing technological and scientific landscape that, like I said, is emergent and necessarily urgent to address. So the core message that came out of the white paper is that education must evolve without abandoning its foundations. We can't just discard the past, we must build on it. And there's a legacy there of science and technology that's really foundational to what we see upon us now that we have to confront and address. So we must train students in classical reasoning and prepare them for frontier challenges at the same time. So there's a dual fluency there. So there's foundational thinking in the scientific method, and then there's also the application of our reasoning and the application of how we think in terms of integration and systems science to address the frontier challenges. And I'll talk more about that in a minute. So the white paper sets the vision, the companion guide delivers the implementation, and it has to be part of a coordinated effort. No one institution, entity or person is ever going to address this adequately. So just the core concept here that foundations still matter, and there are three pillars to this. One is Newtonian dynamics, so we still teach force, motion and inertial frames, and they're still central to spacecraft modeling and orbital mechanics and planetary science. So your gravity, acceleration, your velocity and speed, and angular momentum. So all those sort of things are really foundational and important. And then we've also got thermodynamics and electromagnetic theory. So they're essential for understanding energy and energy systems, communication and classical engineering. So all the technology around us now that we use for communication and for motion and its links to electromagnetism are all foundational concepts. And then the third pillar is orbital mechanics and the scientific method. So students must still learn how to analyze and model systems with precision and with evidence using the scientific method. So just here there are four key concepts around our emerging frontier. And the first is the scalar field theory. So it's a new way to think about motion, gravity and energy. So in other words, overcoming inertia. And then secondly, psionic interfaces, so linking consciousness and control and with blending biology by blending biology with machinery. So there's a real move in industry and aerospace at the moment to look at control systems and even moving beyond holographic interface technology in helmets, for example, and actually looking at just by thinking about an action, you can make a system do what you want it to do. So that's really an emergent and fast accelerating area of science and technology in industry and aerospace. Then we've got transmedium propulsion. So irrespective of the origin of UAP, we have vehicles observed in our air, space and water that move transition seamlessly across them, thus the term transmedium. So there's a real need there, and Energyscapes is at the frontier of this in helping to lead the way and understanding how this propulsion works, how it's linked to scalar field theory and the implications it has for psionic interface technology. So the fourth one is, as a result of that, is field-based energy coherence. So energy transfer through resonance and lattice interaction and not wires. And our lab spends a lot of time looking at UAP and understanding the mechanics behind all that using our analysis techniques and looking at the engineering or reverse engineering of that and the implications it has for technology development. So the integration challenge in looking at foundational and emergent is to think across, to teach and prepare. So we've got from compartmentalized to integrative learning. So students must think across physics, biology and engineering. And I would also add in there chemistry, earth and space science and mathematics, as well as being all linked to one system. So instead of teaching reductionist models and siloed topics, we've got to move to systems synthesis. So teach how elements interact dynamically and not in isolation. So we're not sitting in a physics class going, why are we doing maths? We're not sitting in a chemistry class going, this isn't physics. It's got to be integrated to understand this whole paradigm shift in thinking and systems level technology that the job market is going to have a big demand for now and into the future. So we've got to prepare by moving from static knowledge to dynamic curiosity and prepare students to ask better questions and not just memorize facts. So it's moving away from this post-industrial siloed topic setting in the high school environment to an integrated curricula where subjects are orientated more around the need to think and the need to apply technology and understand systems in this new paradigm that's upon us. So the strategic framework around that is to bridge, encourage and use. So we go from classical core settings to bridging concepts and then to emerging science, and we talk a lot more about that in our white paper and our companion document. So it's using classical knowledge as a base and building with bridge units and frontier ideas on this. And to achieve this, we have to encourage flexibility and fluency across domains. So we need to promote thinking that is both analytical and imaginative. And so we don't have these siloed topics where we're not cross-fertilizing subjects, because that is a growing need there to achieve that, to understand this paradigm shift in thinking and technology rollout that is upon us now. And we want to use real phenomena or UAP case studies. So we need to look at waveform matching resonance events and inspire deeper inquiry into the underlying mechanics, science and engineering behind this and its implications for technology development that we see starting to come out publicly in industry now. That's irrespective of whether it was always clandestine or in the private sector and kept separate from society. There's a real need now to understand how all this works as it's rolled out in the public domain, and the education sector is in an emergent landscape where there is a need to catch up with this relatively quickly, I would say. Now, the role of educators and institutions in that regard is to provide, build and foster. So the white paper talks about providing continuity while enabling transformation. So we need to support both traditional science topics and their transition in the classroom environment. That's moving into that integrated systems level thinking school layout that we've been talking about. And then build conceptual scaffolding toward the unknown. So teachers are guides and not just content experts. So in terms of systems level thinking, you can be a subject matter expert, but that's not necessarily relevant in what we're talking about in this paradigm shift, because it's walking into the unknown and dealing with the complexity of systems level thinking. And that's a combined effort by a lot of different people in different areas. So it's being able to think across subjects, integrate them into a systems dynamic within a high school classroom setting. So we need to foster cognitive flexibility and ethical imagination amongst our school leaders, institutions and our educators, and prepare students for novel challenges with responsibility and creativity. So preparing for these new industries, and we discuss this in the white paper and the bridging or companion document. So aerospace propulsion, so students must be ready to design, test and manage advanced flight systems linked to this paradigm shift. We need to look at field-based transportation systems, so energy efficient, environmental responsive or environment responsive vehicles of the future, and that's the scale of field technology that's upon us now. Now, in that regard, we need to look at neural machine interaction. So there's a real big shift at the moment to look at computer interface technology and this whole psionics concept of thought as determining action without even any wiring or not even wireless control. It's the ability to interface neurally with machines just through thought and action. So linking human cognition with interface systems. And then lastly, scalar energy and planetary infrastructure. So from mining asteroids and other planetary bodies to tapping Earth's energetic lattice. So Energyscapes does a lot of work looking at the application of reverse engineered technology in industry and in particular mining, and that's both on planet orbital mining and mining other planetary bodies, and the systems that are needed to sustain that and support that beyond your traditional fuel-based propulsion industries. So really looking at scalar technology and the advantages that has for industry that's working in extreme and hostile environments on Earth and out into the solar system and beyond. So just briefly, the companion guide, which I'll talk more about in a separate presentation. So it looks at discipline-specific lesson plans, detailed roadmaps for physics, chemistry, biology, and more, and how they are cross-linked. So we have an outline for full curriculum modules in that regard. So there's hands-on student experiences explained in terms of spectroscopy, psionics, and field experiment or resonant field experiments in that regard, and an implementation roadmap too, from teacher training to pilot scaling across systems. So that companion guide really brings together and builds on the core concepts outlined in our white paper. So just a call to action in terms of this, because as I said, this is an emergent and urgent paradigm shift in thinking that is upon us now. If you follow the worldwide efforts in terms of the disclosure movement, the United States Senate hearings, different countries and their calls to action within parliament or governance structures in terms of dealing with what's going on in our skies and on and under our oceans, and the implications this has for humanity and society, irrespective of their origin, and whether or not the technology has already been worked on in the private sector through our government aerospace contractors. There's more of an openness now to address this and to come on board with the people already involved and really shift our thinking into the future and the ethical and sensible use of this technology. So we've got support educator transformation, so provide training and time for teachers to explore new content areas, fund pilot curriculum implementation, so help schools test this model through supported innovation, and promote public discourse in this whole area. So we need to normalize the discussion of scalar, psionic and field-based sciences. So it's really shifting this whole pop culture narrative of UFOs and UAPs to more of a scientific discipline and building an understanding of the missing science around all this, because there is a science, and Energyscapes Lab has spent or relentlessly looked at and spent the last 5 years uncovering the science behind this and the implications it has for our society. And connect with industry in that regard, so linking the classroom content to industries to do with energy and defense in particular, and of course aerospace. And these are all industries that are really starting to look closely at this in the public domain as this technology comes out and becomes more readily available for its adoption and use across society as we move off the planet and out into space. And thus the importance or increasing importance and demand that we really get movement in our space science curriculum into this whole domain as it unfolds around us. So just to conclude, this is not just a white paper, it's a bridge from the known to the emergent the emerging. It's really about walking into the unknown, embracing, accepting and moving in the unknown at a systems level of thinking. So we're moving from between classical rigor and new horizons. So it's a continuity of curiosity and capability development. So keeping the foundations and the fundamentals of space science curriculum across the topics in a high school setting, but really looking at developing our capacity and capability to meet the demands of industry that is emerging around us now. So it's preparing the generation that will not only understand space but reshape how we move through it. And that's really important, moving off planet and out into the solar system, is accepting that there's still a place for our traditional energy systems, combustion-based propulsion systems, and all the technology around that, which really sits alongside the need to move large numbers of people, equipment, plant, and infrastructure around the planet into orbit and off planet and out into the solar system. And the technology to do that is upon us now, and we need to prepare now for what is going to happen. So once again, thank you for listening to this. Our next presentation will look at the companion document that goes with the white paper on this whole concept. You can find a lot of our research around the science behind all this on our ResearchGate profile, EnergyScapes Lab. LinkedIn has a lot of information that's put out in the public domain about all this, and of course we have a YouTube channel where we present on all this as well. So thank you very much for listening, and we'll talk again soon and discuss the companion document that goes with the white paper and this presentation.